Hello and welcome back. Let's roll some barrels. So Tane works weekends unloading barrels. Excellent. In one instance, he rolls an empty barrel with some mass and some radius r down a ramp at some initial height, 1.34 meters. The linear speed when it reaches the bottom, oh wow, look at that perfect circle. The linear speed, v, is 3.4 meters per second. Part A, describe the energy changes that take place as the barrel rolls down the ramp. Alright, well, what does it start with? What energy? It's got some height, right? It starts with gravitational potential energy. So EP, or we could write GPE to be clearer, because EP could also mean elastic potential, or just potential in general. So GPE, you don't need to write it out in full, you can use shorthand, that's fine. Does it start with kinetic energy? Technically, right, if he pushes it to get it moving, like yes, but you know, that's not what they're looking for, so let's just move on. And then what does that potential energy, gravitational potential, convert into? Well, it starts moving, so it's got kinetic energy, and it's translating, so it's got linear kinetic energy, and it's rotating, so it's got rotational kinetic energy. And are we done? Yeah, I mean, if it's part way down the ramp, it's still got some potential, right? And it would have lost energy to heat, but once it reaches the bottom, there's no more potential relative to the ground, and in this case, it's safe to ignore heat losses. And that is an achieved question, right? Just making sure that you acknowledge, instead of in level 2, when its potential goes into kinetic, we have two types of kinetic, right? One for linear, so just straight line movement, and then one for rotational. Alright, and that leads us nicely into part B to calculate the rotational inertia, so capital I, of the barrel. They've given us a hint, how gracious of them. Calculate the gravitational potential energy at the top, EP, and the angular velocity, so angular velocity is omega, at the bottom. And assume no energy is lost due to friction. Okay, great. And so let's do what they say. Let's work out the gravitational potential. Can you hear my cat snoring? That is the question. Oh my gosh, quite loud. Let me, nah, she can sleep. She can sleep. You guys don't mind. So the gravitational potential energy, mass of the barrel, which was 5.5 kgs. 5.50 times gravity, 9.81 times height, is that 1.34? Yep. 1.34 meters. And that gives 72.3 joules, right, for energy. So that's the energy it starts with. And of course, that is going to convert into linear and rotational kinetic energy. Okay, so thinking about it, we know the final velocity, translational velocity, so we could work out the linear kinetic energy. However, the rotational kinetic energy depends on its inertia, that's what we're looking for, as well as its angular velocity. Okay, so let's do as they say and find the angular velocity. We're in our formula sheet, let's just pull that up. Oh, I got rid of it, 1 second. Oh, okay, we're back. Brought up the formula sheet again, so we're looking for angular velocity, so that's omega. And since we have the linear velocity v and the radius, we can find the angular velocity using v equals r times omega. v equals radius times angular velocity, solving for angular velocity, linear velocity divided by radius. The linear velocity was 3.4, and the radius of the barrel was 0.280. 0.280. And that gives us 12.1 radians per second. Right, units for angular velocity, radians per second. Cool. Alright, what's next? Well, going back to part A, we know that potential energy converts into linear and rotational kinetic energy. So let's just translate this into an equation with our known values and our unknown values. So mgh, which we've already worked out, but I'll fill that in a moment, goes into linear kinetic energy plus rotational kinetic energy, which looks similar, but instead of mass, it's inertia, and instead of velocity, it's angular speed. And so that on your formula sheet, I'm so blind, here it is, oh yeah, on the right hand side, EK rot, not for rotten, but for rotational. Yeah, and with this equation, you'll note we know mgh, 72.3 joules. We know mass, we know linear velocity, we just worked out angular velocity, and so the only unknown is the rotational inertia. So substituting in, what happened to my pen there? Substituting in mass, which was 5.50, linear speed, which was 3.40 squared. So this is the linear kinetic energy, but it also transformed into rotational kinetic energy, which is half times inertia times angular velocity, 12.1 squared. Now we have one equation with one unknown being the inertia. So let's just simplify that. Where's my calculator? Pull you over here. So 0.5 times 5.5 times 3.4 squared, 28.9. And it is good to show this intermediate step, because I've just shown the kinetic energy, the linear kinetic energy, which is actually a merit point. So if we stuffed up the final answer, but we showed this intermediate answer, we can still get good credit for it. Plus half times 12.1 squared, 12.1 squared, 73.205 times I. Yep. And then we can subtract 28.9 and divide by 73.205, which would give us, let me just look at the mark scheme, 0.553. And since I don't trust the mark scheme all the time, let's double check. 72.3, take away 28.9, divided by 73.205. Oh. Yeah, so this is why we don't trust the mark scheme. Yeah. So I would say rounding in the mark scheme would have been preemptive, or maybe I did it preemptively. But regardless, you get either of those answers. And what are the units for inertia? How I remember it is I always remember this equation for inertia, which is for only specific shapes, but it's mass times radius squared, so kilograms times meters squared. So our inertia is in kilograms meters squared. And that is an excellent answer. Let me just pause the video right now and check if I can find the mistake. And I found the mistake. It was in this calculation, which I was just telling you guys to show your work. That's embarrassing. So my calculator, I either put it in wrong. Oh, where's my calculator? Regardless, that should not be 28.9. It should be 31.8. And if you follow that calculation through, you get what the mark scheme did. Yeah. Which again is a great lesson to show you're working. Even though my number was incorrect, the marker can see the process was correct, and sometimes they accept like a minor error in your calculation. Yeah, sometimes they don't, but it's better to show you're working. All right. In summary for that one, starts with potential energy, which we worked out, converts to linear and rotational kinetic energy. So we needed the angular velocity, and the only thing unknown in this equation right here was inertia, and we solved for that, hopefully correctly. Let's move on. So Tane then sits on a swiveling stool. So I hope you got the chance to do this practical whatever school you're at, holding a full bottle of water in each hand. So he starts with his arms extended, definitely to scale, and then he pulls his arms in, and he notices as he pulls his arms in, he spins more quickly. When he puts his arms out, he spins more slowly. So explain the reason for this. So this is a classic angular momentum question. So let's start by saying we assume momentum is conserved. Assuming no external, instead of forces, we can use the word torques because it's rotational motion now. But you could say forces as well. Assuming no external torque, angular momentum is conserved. Cool. I'm just going to remind us of this equation. Angular momentum depends on inertia and angular velocity. So let's consider the two positions, right? Arms are out or arms are in. So when arms are stretched, how is his rotational inertia affected? So recall, inertia depends on how mass is distributed from the center of rotation. So for Tane, his center of rotation would be sort of in line with his body. And we can consider the mass of the water bottles. And as that mass is further away, right, it's distributed far from his center of axis of rotation, his inertia is high. So when arms are stretched, mass is far from rotational axis, so inertia is large. Great, so he starts with a high inertia, and now let's consider what happens when he brings his arms in. When arms come in, what happens to the inertia? Inertia decreases, and I'm not going to re-explain it because I've already explained why the inertia was large, so it's sort of the complement of that for why it decreases. So when arms come in, inertia decreases, angular momentum is constant, right? Because we said assuming no external torques, angular momentum is conserved. So angular momentum is constant, so angular velocity increases. And if you want the equation form of this argument, angular momentum is constant, inertia decreases, so angular velocity must increase in order to maintain that constant angular momentum. Great, and this question is a merit question. And guess what? If the only thing you said was angular momentum is conserved, you would get an achieved point. So just understand the question is asking about angular momentum, state the assumption, and then try and explain it the best you can. You're effectively explaining this equation. Well, I guess, and the inertia equation too. Yep. All right. And lastly, Tane spins with an angular velocity of 3 radians per second. When he brings his arms in, he increases his speed. Okay, that makes sense. In a time of 4.5 seconds. So this is a rotational kinematics problem because we're given some initial angular velocity, some final angular velocity, and the time it took to reach that final speed. We're asked to calculate his angular acceleration, which is denoted by alpha, and the number of revolutions made in this time. So thinking about kinematics, so that's the equation sort of in the middle, starting from, well, here really. It depends on angular acceleration, initial and final angular velocity, time, and theta, which is angular displacement. So angular displacement is a little bit different to revolutions, right? One revolution, so one rev, would be 2 pi radians, or 360 degrees. So our last step after we find the displacement is to convert it into revolutions. So finding angular acceleration, let's list out what we know. Initial angular velocity, rads per second, final angular velocity, and the time, 4.50 seconds. So we know 3 parameters, which means we can solve for either of the other 2. So looking at our formula sheet, we are looking for alpha. Right, so looking at the first equation, we know final, we know initial, we're looking for alpha, we have t. So let's use that one. It's got everything we know and need to find. So state the equation. You could either put in the values here and then solve for alpha, or you could rearrange it first, then put in the values. I'm going to rearrange it first. So I'll subtract omega I and then divide by t. Alpha equals final, take away initial over t, which is 7, take away 3, over 4.50, and that gives 0.889. Right, to 3SF, as each of the parameters are. And what are the units? acceleration, so it's radians per second squared. And that is the achieved part. Tick. Now let's find the number of revolutions made in this time, starting by finding angular displacement. So looking at our formula sheet, you have a few options. What could we use? We could use the second one, because we know the final, initial, and time. Yeah. You could also use the third one, because we worked out alpha. Could we use the last one? Initial, time, yeah. So you could use all three that have theta in it. I'm going to use the one with the fraction over here, because it's already rearranged for theta, and it doesn't have like a squared term. Yeah, but try them all, they will all give the same answer. So finding angular displacement, I'm not going to list out what we have again because I already have. I'm just going to state the formula, which was final plus initial over 2 times t. So 7 plus 3 over 2 times 4.5. So what's that? 10 over 2 is 5. 5 times 4.5. 20. What's that? 22.5. And units are radians for angular displacement. And if you got this far, that is a merit. Right? Because we haven't quite answered the last point. We need to find the number of revolutions. So to get revolutions, it's the angular displacement, divided by 2 pi. Or it would be divided by 360 if this answer was in degrees. So 22.5 over 2 pi, giving us 3.58 revolutions. In other words, Tane spun 3.58 times in 4.5 seconds to accelerate from 3 to 7 radians per second. That's excellence. And wow, that's the end of that question. All right, speak to you next time.